Today we're going to discuss sampling issues. This is part one of potentially a three-part series of videos. So let's start with the reason why we're doing any sampling at all. Ultimately, a sample is just a tool. We're really not interested in the sample per se. What we're interested in is the population at hand. And that population is going to have a definition that it's going to come essentially from our problem. So if we are interested in young professionals that are, let's say, between the ages of 24 and 32 that have an average income of $80,000 that live in metropolitan areas in the southeastern United States. That is a very clearly defined group of individuals, right? And that's going to be our population of interest, okay, in this example. Now, what oftentimes is going to happen is that collecting information or data on this group of people, on our population, it's going to be costly and time consuming, especially if the group is large or geographically spread apart, right? It's going to make data collection more difficult. So oftentimes, instead of doing a census, which is basically asking or collecting data on everybody in your population, that is a census or enumeration, right? Everybody gets either observed, measured, or asked. And because of time and cost associated issues, oftentimes what we do is we ask or measure only a subset of that population, and we call that subset or small part or smaller part of the population a sample. Okay, so as you can see, this will be our population of interest, whatever parameters define it, right? And then from that, what we're gonna typically do is use some mechanism that enable us to select a subset of that population. So given that we're considering both a sample and a census, let me walk you through the advantages and disadvantages of both. In other words, when should you lean towards using a sample versus a census? So like we were discussing before, the most obvious answer is a census is probably going to be more time consuming and costly. So if budget is a concern, uh, typically when you have a small budget, you're going to gear towards a sample, right? Because it is more economical to only ask a subset or only measure a subset of the population. Whereas when you have a large budget, you might consider a census. Also, like I was saying before, collecting a subset of the data is going to be faster. So if you need to make the decision quickly, a sample is going to be more appealing than if you have more time in your hands where maybe you can consider the higher accuracy of the census, at least potentially. Okay. Then another thing that matters is the population size. Oftentimes in business to consumer markets, we have really large populations, and in those situations, oftentimes we're going to use a sample. On the other hand, in business to business, there might be situations when you only have 10 or 15 potential customers because there are only large firms that are buying your products or services. And because of that, a census might actually be reasonable. Maybe ask all 15 companies or managers that work at all 15 companies that are potential customers for you. Okay, the amount of variation that is within the sample also matters. If there is very little variation, a sample is going to be more appealing. The rationale for this can be understood if it's not very intuitive by thinking about the extreme case where there is no variation at all, meaning the variable that you're trying to measure, and I say variable in quotation marks, and it's a constant because everybody in the population has the same value. So for example, if you're interested in males or females, I don't care, but just one of the two genders, and everybody in your population has the same value for that variable, right? Let's say female, to not upset anybody, or maybe upset some people. In a situation like that, collecting A sample of 1, if you're interested in measuring gender, it's all it takes, right? Because everybody has the same value. So once that you observe gender for one individual in the population, you're done. An extreme case, which will be a polar opposite, is when everybody has a different value on the variable. Then you're going to need a much larger sample, or in the extreme, you will go for a census. So if you have large variation, you're going to use a census, or if you want to get in between really large samples. Okay, and then finally, one thing that we haven't discussed a lot in class, because this tends to be more of an engineering aspect, is that sometimes the measurement action, or the fact that you're measuring something, might actually entail destroying products. Typical example of this will be light bulbs. If you're trying to look at durability, for you to test durability of the light bulb, you need to wait until it burns out, which is a bummer. If you do it with oil production, then you have nothing to sell, right? So those are destructive measurement actions or ways of measuring. And if you're using a marketing example similar to this, it will be, for example, a taste test, right? If every product that you produce goes towards tasting because you're trying to measure satisfaction as a census, and that's not going to work very well, right? So if you have a destructive method of measurement, you're going to always use samples. And on the other hand, if it's non-destructive, you could consider at least a census. So let's discuss quickly how we'll come up with a sampling plan. So the first step in the sampling plan is just given from the problem definition that you should have already handled before you're thinking about any sampling, which is, what is your population of interest? Now, we already gave you an example on the previous slides, but let me give you a different example. What is very important in this step is that you clearly delineate who is inside of your group of interest, which we're going to call the population, and who is outside. So it might look like something like this. It might be that you're interested in females that are between the ages of 17 and 25 that dye their hair on a regular basis and that live within the United States. So that's a clearly delineated group of individuals, in our case probably potential customers. Okay, and this definition is important because we're going to see how a lot of the tools that we need to develop the sampling plan are going to be dependent on the definition of the population. Remember, at the end of the day, the plan to collect the sample, it's only to learn about the population. So this is an important step. Then after that, what we need to do is decide how data is going to be collected. We have already talked about different mechanisms for data collection, from observation to experiments to surveys. Also, you have to consider the contact method. Is it going to be in person, online, via phone, etc.? Okay, all these aspects are important because the sampling might actually require specific information for the sampling to happen in reality. For example, if you want to do an online data collection, your sampling frame, which we're going to discuss in a minute, it's going to need information like an email address that is going to enable you to directly contact the people within the population. Okay, good. Now, after you know how you're going to collect the data, what you need to do is come up with a sampling frame, or acquire or construct a sampling frame. What is a sampling frame? It's a list of every individual that is part of your population with an identifier. It could be a name, it could be an ID, it really doesn't matter, something that is unique. And the second piece of information that is going to be very important for us is one way in which we can measure that individual. When I say individual, it could be a firm, it could be a family, okay? Some sort of subject that we're interested in measuring, okay? So you can think about this as a spreadsheet in Excel that has all the names of the individuals in your population with a way of contacting them, like an email address, a telephone number, or an address, okay? And this is very important. And oftentimes it's gonna, basically we're gonna have to go out of our way to either construct this or ask a firm to secure a list like this for us. And that might usually mean paying money for it, okay? Then after we have our sampling frame, what we're going to have to do is devise a mechanism that enables us to draw from that sampling frame a certain amount of people or individuals or firms, right? Whatever unit of analysis we have chosen. Okay, so we're going to have to, and we're going to discuss in class 5 or 6 different mechanisms that you can use to select people. Some are going to be random, some are going to be non-random. We're going to see the pros and cons on both. And then finally, you're going to have to decide the size of the sample. Not all samples are created equal, and we're going to give you some guidelines and formulas that enable you to decide how large a sample needs to be for you to be able to accurately decide on what values the variable of interest takes in the population. Now, let's backtrack 1 minute. Remember, at the end of the day, what we're interested in is in the population. Now, this population is going to have some characteristics, and those characteristics we're going to call parameters. Like, for example, if you are interested in measuring satisfaction for females that are between the ages 17 and 25 that live within the United States and dye their hair at least once a month, right? That will be the population of interest. And there is going to be an average level of satisfaction with the dyeing product that they use on a regular basis, that if you could ask everybody in the population, whatever number of million of people fall within that population in the United States, you could compute some sort of average satisfaction score. All those values at the population level, they are typically going to be denoted in Greek letters because we do not know their values, but it's what we are interested in. And these are called parameters. These are characteristics of the population that are unknown to us, but that we would like to learn about. And what we're going to do is we're going to use samples to do that. So we're going to use a sample to learn about the population. And the way we're going to do that is to learn about the parameters, which is the characteristic of the population that we do not know. We're going to use a statistic. What is statistic? It's some computation that is done on the data that we collect in the sample. The simplest example that I can give you that I know you're familiar with is the sample average, which is if you have 3 observations, add the value of those 3 observations. In this case, it will be satisfaction for females between the ages 17 and 25. Within the United States, let's say that we have a sample of size 3. The sample statistic will be to get those satisfaction scores, add them all up, there will be 3 of them, and then whatever output you get, divide by 3. That will be a sampling statistic, okay? That statistic is going to change from sample to sample, okay? And it's trying to give you an idea about what's happening in the population level. Now, we don't know the population value because we don't have a census. If we did have a census, we will know this value, but usually we're not going to be in this situation. So I want you to realize that the value in your sample of whatever you're trying to guess is going to be different typically from that in the population. And that difference we call sampling error. This is an error that we incur or happens because we collected a sample instead of collecting information about the entire population. And we need to acknowledge that this exists. Now, the nice thing about sampling error, as we're going to see later, is that there had been about 300 years of very smart people thinking about how to deal with this sampling error, and they have developed a branch of statistics called inference that enable us to make assertions about the population, even though the only thing that we know is statistics from the sample. Okay, so we're going to leverage all this hard work and all this formula that have been built over literally 300 years, maybe more, and so that we can make this assertion. So we're going to jump from the sample to the population, standing on the shoulders of giants and statisticians, basically. Okay. Now, what I did not mention here is this sampling error. It's going to become smaller and smaller the larger the sample becomes. This should be obvious, but I'm going to show you with actual numbers in a few slides that this is actually the case, not just an opinion. Okay. Is different from non-sampling error. What kind of non-sampling error can you induce? There are many. A typical non-sampling error will be measurement error. We've already discussed this a little bit, and when I talk about measurement, I'll get into more detail about how to deal with measurement error. Now, there are two different types of sampling mechanisms that we're going to discuss. Okay, one is going to be probability sampling, the other one is going to be non-probability sampling. Now, let me explain what each of them are generically, and then we're going to get into the specifics for both of them, where we're going to discuss at least two types of probability samples in detail, maybe a third one in a little bit less detail. And we're going to discuss 4 different non-sampling mechanisms. Now, in a probability sampling mechanism, what we have is we have a known probability of all the units in the population. And by the way, it doesn't have to be the same, okay, but it is known a priori before you actually sample. What are the chances that any of them will be measured? Okay, and this is important because this is going to enable us to use inferential statistics to make assertions from the sample to the population, which is a big leap of faith. You need to understand that. The sample is not the same as the population, so whatever you're learning from the sample, moving it to the population level, it's a complex and risky, in a way, assertion. So you need to be careful with that. So what probability samples buy us is it enables us to generalize from the sample to the population, which is the whole reason why we started with this exercise. We don't care about the sample, we care about the population. This is why probability samples are so valuable. What they do to enable us to generalize is they measure specifically how much sampling error there is. And once that you measure it, you can acknowledge it. So what you're going to do is you're going to either build a test that is going to tell you whether something is likely to be the case or not in the population based on this sampling error. As we're going to see, we're going to do a lot of this testing later. Okay, or construct a confidence interval, which is going to give you a range of values that you expect the true parameter to be in the population. Okay. Now, what are the downsides of probability samples? As you can imagine, it's not all positives. The biggest downside is expensive, complicated, requires knowledge of statistics, and it requires knowledge of experimental design sometimes. Anyway, and there's no free lunch, but it's definitely of the two methods, the one that has better properties for what we're trying to do. Now, what is a non-probability sample? These are samples when we do not know a priori the odds or probability that any of the elements in the population will be chosen. Now, this is something that is usually done because it's inexpensive and quick. And the downside is you cannot use inference. I mean, you can, but there is no solid ground that you're standing on to use any inferential tools like testing or confidence interval building. And you are likely to get biases introduced that basically are going to give your answers a low probability of being accurate to the population level. So we'll see when these things are used. We might use some of these in our case because we have limited resources, and it's better to have some data than not data at all. But there are limitations, and you need to be aware of them. So here are the different sampling methods that we're going to discuss in class. Like I told you, there are two big families. On one hand, you have over here the probability samples, which are the ones that have the nice properties that I was discussing before, okay, which is that you're going to be able to generalize to the population, and the downside that they are more expensive, time consuming, and they require technical knowledge. On the other hand, you're going to have the non-probability samples, which are going to be mechanisms that enable you to collect that data maybe easier. For example, convenience sample, when you ask people that are likely to answer, like for example, your coworkers, or in your case, maybe your classmates, right? The downside of that is it's very hard to generalize to the population because your classmates might not be all the same as in the general population that you're interested in. So you're going to have some issues, but the upside is it's more convenient and usually efficient. So let's start discussing the different probability sampling methods. These are the ones that are less intuitive but have better properties. So let me walk you through the easiest one of all the probability sampling methods, or at least the most intuitive, which is called simple random sampling. Okay. Now, simple random sampling is basically when every unit in the population has the same probability of being chosen, right? So if you have 100 people in the population, the probability that any of them will be chosen, if you're collecting a sample of size 1, right, will be 1 divided over the size of the population. Okay, so in this case, 100th, so 1%, if you have a population of size 100. Obviously, if your sample size is larger, right, the probability that any given unit will be chosen at random will go up. So if you're collecting a sample of size 10 out of a population of 100 units and you're using simple random sampling, the probability that you'll choose any of the units is going to be 10, which is the sample size, divided over 100, which is the population size, and that's going to be, in this case, 10%. Okay, I think this is the most intuitive of all the sampling methods. Okay, it's also fair, which everybody likes because everybody has the same chance of being chosen, but it's not efficient. And this is something that is not intuitive. Okay, there are more efficient methods or more efficient mechanisms that you can build or construct to draw from the population other than being agnostic about the units and treating everybody equally. Okay, so the nice thing about this, it's easy to understand. The downside is not efficient. So I already gave you this, right? I told you that simple random sampling, easy to understand. Every unit has the same probability of being chosen, simple. You can use inferential statistics because it's a probability sampling method. So you can take data from the sample and tell me with a certain level of confidence what's going to happen at the population level. We'll do this via testing and confidence intervals. Okay, what are the downsides? Number one, you need a sampling frame. You need a list of everybody that is part of the population of interest, whatever that is. Remember, you need to define that a priori and carefully, okay? And so that you can draw from them, so you can ensure that everybody has the same chance of being chosen. This is problematic because oftentimes getting a complete list is not possible, okay? Also, it tends to be expensive because these lists that I was alluding to tend to be expensive. You need to acquire them, or you need to construct it yourself, which might be a very challenging endeavor. It might take a really long time for you to collect the list of everybody that is part of the population, as you can imagine. Okay, and of course it depends on the population. The narrower the population, the easier this might be. Okay, and the part that is not intuitive is what I was alluding to before, is that for the same amount of budget, you're going to have less precision in your results than other mechanisms that I'm going to discuss, or you can get the same level of precision with a lower budget, okay, which is something that you can choose. Special way of implementing simple random sampling is systematic sampling. Systematic sampling is when you use a skip interval to select elements from a list instead of using, for example, random number generator, which I will show you in class how to use if you've never used Excel for this before. And what you can do is you can have your sampling frame, right? And hopefully arranged in a way that is somewhat random. You're going to see the issue with this at the end if you don't, right? And then what you can do is you can select a skip interval that is going to ensure that you come up with a sample size of a certain number. So for example, if you're interested in a sample size of 10 units and you have a population of 10, your skip interval will be the population size, which is 100 divided by the sample size, which is 10. So that will be 10. So every 10 units, you're going to select a unit. Okay, maybe starting from unit number 2, right? You need to pick a starting point. Okay, and then you go down every 10 units, select one. Okay, and then you might have to come to the beginning if you don't start from the first unit, because otherwise you'll run out of units for the last selection. But anyway, this is not a big deal for the most part. Now, the nice thing about this is a very simple way of implementing simple random sampling. The problem that it has is if that list, your sampling frame, it has some sort of order to it. So if it's not truly random, what might happen is the people that get selected maybe have a certain pattern behind it, right? So if these are, I don't know, sales, if they are ordered over time, like monthly or something like that, it could be that certain months of the year or certain days of the week sales are higher or lower because you have periodicity issues, right? Because maybe, I don't know, sales of beer are higher on the weekend than during the week. So if in your skip interval, by the way the data is organized, you're more likely to select weekend sales, you're going to bias all the results. So if you're worried about this, you shouldn't use systematic sampling. Now, what are the advantages of systematic sampling? Like I was mentioning before, it's an easy way of implementing simple random sampling instead of requiring using a random number generator to draw people at random. It enables you to basically implement randomness in the assortment already, and then just use the skip interval to select units from a list. Okay, so it's easy to implement, and it enables you to bypass, to some degree, in some cases, the sampling frame. So for example, you can use random number dialing if you are trying to reach people on the phone to enable you to gather data even though you might not have a sampling frame with people and their telephone numbers. Okay. Now, what is the downside? The downside is if this skip interval that you use has any periodicity issues associated with it, the data that you're going to get in your sample is not going to be representative of the population, and this is a potential problem. So now that we have discussed simple random sampling, let me show you how simple random sampling works with an example. And in particular, what I'm trying to show you here is that the amount of error that you're going to incur in because you're collecting a sample, it's going to become smaller and smaller the larger your sample size. This is an intuitive concept, but I want you to see it numerically so that you see that whatever your intuition tells you, it actually happens. Then after this, in part 2, I will show you something that is not intuitive that relates to the same concept. So I'm kind of laying the groundwork for what's to come in part 2. So let's start with an example, small example, so that we can do some computations in class. And this example assumes that your population is just a chain of retail stores. So there are only 5 stores in the entire population. Those are the 5 stores that we're interested in studying because maybe they are the ones we control, right? And as you can see, we have some data for the sales of each of the stores for, let's say, a given month. I assume these are in millions of dollars. So $15 million for store 1, $19 million for store 2. I think you get the drift. Then the second thing is we have measured the size of the stores in square footage, and we have split them between large stores, which are stores that have more than 10,000 square feet in our case, and small, which are the ones that are under 10,000 square feet. Okay, so you can see that store 1 is large, but store 5 is small. Okay, I think everybody understands. Now, let's say that we are interested in sales, okay, or revenue. You can call this revenue if you want. Okay, now in this case, we have a rare situation. We know all the data for the entire population. So this is a census. You can think about it like that, right? A census of the retail stores that I'm interested in, my population of interest. Okay, and in this case, because we have a census, because we have all the data, we can collect the actual mean sales of the population. So what is the average sales in my population of interest? So I will be adding all the sales figures in all 5 stores, which is the entire population, and dividing by 5. And in this case, we get 15.2. Now remember this number because we're going to use it quite a bit. So remember, 15.2 is the value in the population. Notice how mu, it's a Greek letter because usually we do not know this. We're trying to guess it. We're trying to estimate it. Okay, but in this rare case, because I'm making up the data, we actually know it. Okay, so let's continue with the example and see what happens now. So let's draw a sample from our store population, from our stores population. We have 5 stores of size 1. I know that's kind of unusual. Usually you do not draw such a small sample, but I'm trying to show you a phenomena that has to deal with sample size increases. Okay, so let's start as small as we can. The smallest sample size you can have is 1. 0 is not a sample, obviously. So in this case, because you have 5 stores in the population, potentially, if you're drawing samples of size 1, you could draw store 1, you could draw store 2, you could draw store 3, 4, or 5. There is no other stores because there are only 5 stores. Now, if you're doing this and you're trying to estimate sales at the population level, what you will do is you will compute the average with one number, which is the number itself. So I'm just taking the sales, and the mean sales are going to be the sales itself because you only have one observation. So one observation divided by 1, which is the sample size, gives you that observation. And this is true for everybody, or the potential samples I could get. Now, in real life, you're only going to observe one of these rows. You're not going to observe the others. You're only going to observe, for example, this one. If you get lucky or unlucky, however you want to think, lucky or unlucky, and you observe store 1, your best guess about the mean of the population in terms of sales is going to be 15, which in this case is pretty close to reality, but you might get unlucky and get store 2, and then you'll get 19, which is pretty far, right? Now, the error that you are committing, the sampling error, or at least the component of the sampling error, it's going to be the difference between your mean and the true value in the population. Now, this number over here, which is the true value in the population that we saw in the previous slide, 15.2, it is something that we do not know. But in this case, we do because we have a census. So we're playing a game, pretending like we don't know all the data and we only get one observation and see what happens. And in this case, the error that I'm committing because of the sample is small, 0.2. Okay. Now let's do the same thing. Let's do the same thing with the second one, just to make sure that you see what I'm doing. Okay. So in the second case, right, if I get store 2 as my sample, right, my best guess on the sales for the population will be 19, which are the sales for store 2. Then the error that I will be committing compared to the true value in the population, which is 15.2, is 3.8 units, which is the difference between my sales for my sample and the sales that are true in the population, the average sales across all 5 stores. Okay, 3.8. And you can do this with every potential sample you get. Now notice, some errors are positive, some errors are negative. So if you add them up, they're going to cancel each other out, which is annoying because we're trying to assess how many mistakes we're making. So we're trying to look at all potential errors, not only what happens when you get lucky with one of the samples, but across all sampling possibilities, essentially. So what we're going to do to avoid this problem is square the errors. What this does is it makes sure that everything becomes positive. So when you add them up, nothing cancels out. And also it makes the large errors even larger. So penalizing heavily cases where you get really far away from the true value in the population. Okay. And when you add all this up and divide by the number of different sampling schemes that you could get any of these 5 samples, right? You get an average mean error square of 32.8. Now remember this number, I will show it to you in another slide later, but this is the amount of error in dollars square. How do I know they are dollars square? These were dollars, these are still dollars, because I'm taking dollars minus dollars, so still dollars. And then I'm squaring the dollars, so these are dollars square. I don't know what dollar square mean, but it's one metric that we're going to use in this case to measure the amount of error that I have in my sample. Now let's repeat the exercise, but now let's select a larger sample. So let's go from sample size 1 to a sample size 2. So we're doubling our sample size. We're going from 1 to 2. So now, because we have a population of 5 stores, remember that, we could observe store 1 and 2, or we could observe a sample that involves store 1 and 3, or 1 and 4, or 1 and 5. Any of these 5 samples are possible. Okay, in real life, you're only going to observe one of these. So maybe you will only observe this row. But now we're playing a game just to see what will happen if we were to observe everything. right? Excuse my drawing. It's kind of hard to do with the mouse. Okay, so there you go. So you're typically gonna only observe that row, but what we're gonna do is we're gonna see what will happen if we look at all potential samples that we could get in this exercise. So we've gone from having 5 potential samples of size 1 to now there are actually more, right? Because you can have more combinations. When you have a population of size 5 and you're drawing 2 from it, there are 10 potential sample schemes that you can encounter, and they are outlined here. Remember, this number is the identifier for the store, so this will be store 2 and store 5. That's what I observed. Okay. So let's work through the math in the first one. It's pretty easy math. Okay, if I get this sample, store 1 and store 2, remember store 1 have revenue of $15 million. Store 2 have revenue of 19. So the average between these two is adding them up and dividing by 2. And because I had 2 observations, 15 and 19. So I get an average sales for this particular sample of 17. You can do the same thing if instead of store 1 and 3, you get store 1 and 2, you get store 1 and 3, right? So in this case, the sales are 15 and 17. When you average them by adding them and dividing by 2, you get an average sales of 16. And like we did with these two, you can do with all of them. Here you have the results. Okay. Now, after doing this, we can do like we did before. Remember, our value in the population never changes. This is what's true in the population. Sales are 15.2 if you were to observe all 5 stores, which you are not going to because you only have a sample of size 2. Okay. So what you're going to do now is subtract this. Usually you won't be able to do this, but this is just to show you the properties, not what happens in reality. Okay, so it's 17, which is what we got from our sample, minus the true value in the population, which is 15.2. You can see that 2 slides back. And that gives you an error of 1.8. And we're going to do like we did with sample size 1. We're going to square those errors just to make sure that they don't cancel each other out when we add them up. Okay, so this is just the square of that error over here, so 1.8 squared. And I'm going to do this for every potential sample that I could have gotten. Okay, Excel helps here, otherwise you're going to have to do a lot of computations. Now what we're going to do is we're going to average those out to see on average how good is a sample of size 2 in terms of the amount of error that we are incurring in, actually error square. Okay, and when you do that, when you look at the mean error square, which is adding all the results in this column and divided by 10 because there are 10 elements in here, or 10 potential samples that we could encounter of size 2 with a population of size 5, we see that the error on average has reduced from 32 units to just a little over 2 units. Okay, this is a huge reduction. So doubling your sample in this case really helps a lot making the errors that we are making because it's a sample smaller. Let's see what happens when we go to 3. So let's see what happens when instead of selecting a sample of size 2, we actually select a sample of size 3. Now, as you can see, the number of potential samples now has decreased because when you have a population of 5 elements, drawing 3 without replacement, which is what we're doing because we don't want to see the same store twice, right? And it can only be like this. It's either store 1, 2, or 3, or 1, 3, and 4, or 1, 4, and 5, 2, 3, and 4, 2, 3, and 5, or 3, 4, and 5. No more combinations are possible that are not the same. So for example, store 3, 2, and 1 is the same as store 1, 2, and 3 because it's the same stores. So I don't care about order, not in this case, at least, because we're just looking at a cross-section of stores. Okay, so these are all the potential sampling schemes that you could have, drawing 3 units out of a population of 5 stores, like in our case. And like we did before, I'm going to do the same exercise. I'm going to take whatever sample I have. I'm going to look at the sales for each of those stores, which are store 1 is 15 million, store 2 is 19 million, store 3 is 17 million. I'm going to add these 3 up and divide by the number of elements that I have in my sample, which is 3. And I'm going to get an average guess about what's happening in the population, in this case, with my first sample of $17 million, which again, in this case, because I know the true value in the population, which will not be the case usually, I can see that I'm committing an error of $1.8 million. Okay, and when you square that so that we can add them all up, I get 3.24 million square. Okay, so here we go. We have done the same thing for all of them, and again we compute our mean error square, and when you do this you get a value of 1.7. If you remember in the beginning when we have a sample size 1 and the mean error square that we were getting, actually you can see it here, that way you don't have to remember. When we had a sample size 1, the mean error square that we were getting was $32.8 million square. And when we increased the sample size from 1 to 2, we decreased that error dramatically to $2.486 million square. And now when we increase it to a sample of size 3, it shrinks even further to 1.7. So what you can see here is if you're concerned about sampling error, all you need to do, which might be expensive and time consuming, is increase your sample size. And in the end, if you match your population, meaning if you collect the census, your sampling error will go away. That's all I have for right now.